Well, dear student, this is Sarshad Hussain. Today we shall discuss the locomotion in the protozoa. If you remember, we have discussed that there are four types of locomotory organelles in case of the protozoa: Seedpodia, Flagella, Cilia, and then the myonemes. So accordingly, there are four types of locomotion also. If it is taking place with the help of the Pseudopodia, it is called amoeboid movement. If it is taking place with the help of flagella, it is called flagellar movement. If the movement is taking place with the help of cilia, it is called ciliary movement. Or with the help of myonemes, it can be called the gliding movement. All these four types of movements have their own speed. Amoeboid movement takes place zero point 0.2 mu to zero point 0.3 mu per seconds. Flagellar movement 15 mu to 300 mu per second, and ciliary movement 400 mu to 2000 mu per second. And gliding movement don't have certain speed. It is not measured, or it is not significant to measure it. First of all, let us see the first movement, that is the amoeboid movement. So because the pseudopodia are present in the sarcodina, so amoeboid movement is also present in the superclass sarcodina. Then Mastigophoran and the sporozoan protozoans, they are again the classes. Sometimes they are called the superclasses of the protozoans. They also show the amoeboid movement. So amoeboid movement is takes place with the help of pseudopodia. You can see I have shown you during the structure of the pseudopodia that a finger-like projection is called the pseudopodia. Now, if you look at this anterior end, there are so many pseudopodia. This is one pseudopodia, this is another, this is another, this is another. No, it means this amoeba is moving towards this direction. The direction in which the amoeba or the protozoan wants to move, in the same direction, the pseudopodia will be formed. There are so many pseudopodia in the direction of movement are formed, but eventually, ultimately, it is the pseudopodia which is longer than the other which will help in the movement. Rest of the pseudopodia will, because they are false feet, they are not permanent structure, they will go away. Now, how this pseudopodia is formed, you might have remembered that during the pseudopodia structure, we have shown you that it is formed by the flowing forward of the cytoplasm. So there are so many theories which explains how this pseudopodia is formed and movement takes place. But among them, the Sol and Del theory, are also called the change of viscosity theory given by Hyman in 1917, is widely accepted theory. Let us discuss how this theory explain how the movement of amoeba, because it's an example of amoeba, or the protozoans with the help of the cytopollia takes place. Now, I have already told you that Hyman 1917 given this theory, and this theory was supported by Pentin and Mast in 23, 26, and 1925 respectively. So basically, the amoeboid movement takes place by change in the consistency of cytoplasm. Consistency of cytoplasm means, if you look at this cytoplasm has outer gel-like structure and then inner sol-like structure. Gel-like structure is little bit rigid one, and sol-like structure is more liquid. structure. So this viscosity, that is, here it is more liquid, here it is less liquid, basically it changes from one to another. So it is the change in the consistency of this viscosity that the movement will take place in the pseudopodia will be formed. Okay, and you are well aware of the fact that cytoplasm has two portions. Outer one is called as ectoplasm, and the inner this one is called as endoplasm. Okay, endoplasm is further distinguished into outer stiffer gel-like region, the plasma gel. So I have already told you this is the gel region. This is little bit stiff. ये थोड़ा सख्त है. And inner one, the plasma gel, which is more fluid region, also called as plasmosol. In order to understand the sol gel theory, you must have this clear picture of that there is an outer gel which is rigid and then inner sol which is little bit liquid portion. Okay, what happens how the pseudopodia is formed? Now you assume that this is an animal. It has to move in this direction in the row, in this direction in which the arrow is showing. Okay, what will happen in the direction in which it wants to move in that side of the animal? Though there will be the liquefaction of the gel. You can see here the gel is not present. Gel is present over here. Sol is in between, but here what has happened that the gel has liquefied into sol. Because gel is rigid, sol is more liquid. Once this rigid layer at its anterior end has broken away, what will happen that the sol, the liquid will flow in this direction because it has no restriction of gel over here. As a result, more liquid will go to this side. As a result, due to the force of this movement of the sol in this direction, because of the absence of gel in this direction, the bulge will appear in the direction of movement, which will form the pseudopodia. At the same time, what will happen? Because here the gel is liquefied into sol, but total amount of gel in the sol must remain constant. So at this portion, this liquefied sol again gets converted into gel. This is called as gelation. Okay, then what happens at the posterior end? So if at this end the sol is becoming gel, then we have to make it that the gel and sol must remain in equal proportion. At the posterior end, gel is getting converted into sol. This is called as solation. So this is how that liquefaction of the gel into sol pave a way forward for movement of the sol in the direction of the movement, thus pushing the plasma membrane for formation of the pseudopodia. And in order to maintain the total quantity of gel and sol same in the cytoplasm, the gel, the sol first get converted into gel, that is called gelation, and at the opposite end of the movement, the sol get converted into gel get converted into sol, called the solation. Now what happens? Because this was the portion where the gel was broken, so for the liquid to flow in this direction, there was no restriction because restriction was ultimately put by the gel because gel is a little bit rigid. No, here the gel is present. So it means the sol present over here is under great tension. It is under pressure of the gel. That gel is not allowing it to move here and here. So whole of the pressure get gets built into the direction of the movement and the sol moves in that direction. As a result, of which the force pull the plasma membrane and form the Seedpodia. At, at the direction of the movement, the surface touching the substratum, the plasma membrane touching the substratum get attached so that the solid can move forward and the plasma membrane may brought forward for the formation of Seedpodia. Okay, this is how that the gel and cell theory explain. At the same time, from the posterior end, the opposite end of the movement, the plasma membrane and the cytoplasm get constricted. Because of the constriction of this portion and elongation of this portion, the cell may move from this direction to this. This is how cell and gel theory explains the movement of this the protozoan with the formation of the pseudopodia. Then the next movement is the flagellar movement. So, because flagella are present in the mastigophora, so the flagellar movement is also taking place in the mastigophora. Two types of flagellar movement is there. One is called as pedal stroke, other is the undulating motion. Let us see both of them one by one. This is the pedal stroke. So what happens over here? This is the organism. This is the flagella. Flagella strikes backward. So this is first position, then it will come to this position, then third, then fourth, then fifth, and then sixth. It strikes backward, but on the lateral side and obliquely. That means not straight way on the lateral side, but in a oblique fashion. This stroke is called the effective down stroke. Okay, and then this flagella start recovering its position to again regain its position which was present earlier. This is the this, this was the original position. So from here you can see it has moved forward from 7 to 8, 9, 10, 11, 12, and 13 position, and again has gained the position which was prior to the effective stroke. So this is the recovery stroke. Recovery stroke is a very passive type of stroke, whereas effective stroke is a very energy taking stroke and very strong stroke, you can say. So when it strikes on the lateral side and obliquely, the the organism moves in the forward direction. This arrow is showing that this animal basically wants to move in the forward direction. Again, it recover the stroke, bring the flagella at this position, and again it will go for the effective stroke. So, in a similar fashion, as you swim in water and strike backward your arm for the movement of your body in a forward direction, in a similar way, the flagella also works. Now, as I've already told you, that the flagella strikes laterally backward but obliquely. Because of this oblique nature, the animal cannot move in a straight way. Oblique nature makes the animal to rotate. As a result, though animal has started from this position, it has reached to this position. Both of them are lying, the starting point and the end point are lying on the same straight path, but it has not reached to this position by a straight path. It has come across it this way. This gyration, this this rotation is because the flagella strike backward obliquely and the animal moves by circulating around a line and reaching to the end point. In addition to this, there are some because if say for example if there is a in this euglena there is one flagella only, in which side it will strike. So it has been seen that it is the position of the stigma, the side of the euglena where this stigma is present, it always strikes at the side of the stigma. Say for example, now the because of the rotation of this, the stigma has reached to this side and the flagella is beating towards this side. So it always strike with respect to the direction of the stigma, that it always strike along the side of the stigma of the cytoplasm. Okay. Then second type of motion is the undulating motion. Undulating motion is similar, very simple. This is the flagella. It is undulating like this. It is not keeping itself straight. After getting straight, it is undulating in this fashion, thus pushing the animal to the backward position. It is exactly in a way if you keep a rope in your hand and then you keep one end of the rope in your hand and then throw it away. So you will see that the undulating type of movement may be seen in the rope exactly in a similar fashion. If the undulation starts from the tip to the base, then the animal moves in a forward direction. If it starts from the base to the tip, then it moves in the opposite or the backward direction. Okay. Then the third type of the movement is called the ciliary movement, the movement that takes place with the help of the cilia. It is exactly like the flagellum, having two type of stroke, the effective stroke and then the recovery stroke. Effective stroke is strong enough. This is the direction of the movement of the animal. So flagella will beat strike backward on the lateral side as well as obliquely, and then it will recover to regain its original position so that it may start another effective stroke. Effective stroke and the recovery stroke are exactly as the swimmer starts uh, giving effective stroke of arms in the water so that its body can move forward, and then recovery stroke to regain the position for another effective stroke. No, again, because the I have shown you that the cilia also strike backward but obliquely. So because of the oblique nature, they start rotating and they start rotating. Say for example, this is the center line. So they are rotating along the center line. The first position, the fifth position is same. It has reached a straight path, but not through a straight path. It has come to this straight position through a rotation path. Now there is a in case of the cilia, because cilia are numerous on the body, there is a metachronal rhythm. Metacronal rhythm means all the cilia of a body do not beat at a time. Say, for example, if this portion of the body is in the effective stroke, at the same time, whole cilia behind it will not be in the effective stroke. When it will complete its effective stroke, another portion, next portion of the body, the cilia of the next portion of the body will start the effective stroke. And then when it will complete, it start recovering and the next will start the effective stroke. In this way, a wave-like fashion can be seen along the body of the ciliates, where the cilia are beating in effective stroke and then recovering in their recovery stroke. Moreover, because the cilia are present on a body in a rows, so I have already shown you that all the cilia of a row do not beat simultaneously. But if this is the portion where many rows of the cilia are present, so this circle or this portion, at this portion the effective stroke will take place along whole of this portion. That doesn't mean one row will uh, go for the effective stroke at this position, then after that next row will start. No, at the same position the effective stroke may start in all the rows, but it will not go up to the end of the row. When it will start recovery, the next effective stroke will begin. This is called as metacronal rhythm. Now, if the animal wants to move in this direction, then the effective stroke will start from here. So, in anterior, if it wants to move in the forward direction, the effective stroke will start from the posterior portion of the body, and if it will move in a backward direction, then the effective stroke will start from the anterior direction. So it is always a vice versa position, you can say. Now, then comes the fourth type of movement called the gliding movement. Gliding movement is very simple movement. Now, here what happens in this? The myonemes, I have already shown you that the myonemes are basically the contractile fibrils which contract the animal just as our muscle contract. Okay, they the gliding movement is again shown by the flagellates like Euglena also, some sporozoans also at certain stage of life cycle. If they are not showing the gliding movement all the time in their life cycle, at least some stage they must show. This movement is called wriggling also because it is exactly like the walk. जिस तरीके से कीड़ा मिट्टी के ऊपर चलता है, ये उस टाइप की मूवमेंट है. और पेरिस्टाल्टिक मूवमेंट भी इसको कहते हैं या ग्रिगोरियन मूवमेंट और मेटाबॉलिक मूवमेंट. Contractile myonemes present in their pellicular walls are responsible for this type of movement. Now, what happens over here if you look at this is the peristaltic movement. It has started from this portion, anterior portion. The portion where the peristaltic movement will start, it will shorten and widen. So, for example, at this juncture, this portion is widened. Then the movement has passed slightly posterior. This portion has widened. Then the movement has started slightly posterior to previous one, and the previous portion has widened, and at last the base has widened. Anterior one is narrow, whereas at the start posterior portion was narrow, anterior was wider and wider and shorter. No, the posterior is wider and shorter, anterior is narrow. So in this way, a peristaltic movement may start from anterior end and progress towards the posterior end, and then brings the animals in a wriggling fashion, as the earthworm you might have seen wriggling on the sand, on the floor, or on the earth. So this is the you can say the peristaltic movement, or also called as gliding movement, which is shown by the Euglena itself. Thanks. This is all about the types of locomotion in case of the protozoa.